Right. Suppose there's an extended object O placed in front of a lens. Let's assume this lens is a converging lens. Converging lens will have a positive focal length. And since object is on the left side, okay, it's a real object. Rays from the object travel towards the lens. So incident rays are traveling to the right. So anything to the right will be considered positive. Any distance to the left will be considered negative. Okay. And since focal length is greater than 0, this becomes the primary focus. Okay. This becomes the focus for this arrangement. Okay. Now our aim is to draw the image formed by this lens and derive an expression for its magnification. Fine. How do we draw the rays to get the image formed when the object is an extended object? What did we do in case of mirrors? To locate the image position, we need two incident rays and we need to trace them after refraction also. Okay. How did we take the two incident rays in case of reflection from a mirror? Which are the two incident rays that we considered?
One is parallel to the principal axis.
From any one point of the object, let's say from the tip of the object, this topmost point, we take one incident ray parallel to the principal axis. What happens to the incident ray which is parallel to the principal axis? Generally,
It meets at the focal point.
it passes through the focus. Okay, basically that is how focus is defined. No, focus is the image position when object is at infinity, or you can say if a ray is incident parallel to the principal axis, after reflection or refraction, it passes through the focus. Okay, so we can trace one of the rays like this. Fine. We need one more ray from the same point and we have to trace it after refraction so that we can get the final image position. Can any of you tell me how to take the second ray? In case of a mirror, we used to take the second incident ray directly to the pole of the mirror like this, such that it gets reflected symmetrically. It was easy to trace the reflected ray this way in case of reflection. Now, how should we take the second ray? Can we take it through the optical center of the lens? Okay, for a lens, we
Yes,
call
sir.
this point as optical center. We don't call it as pole. Okay. Suppose a ray is incident directly at the optical center of the lens. How does it pass after refraction?
Not deviated, sir. It doesn't get deviated.
It doesn't get deviated. It passes without deviation and it meets the other ray here. And this is where the image forms. That's all. That small arrow is the image. Okay. So we take one ray parallel to the principal axis. It passes through the focus after refraction. We take the other ray through the optical center of the lens. That ray does not undergo any deviation. There is another way also to do it. You can imagine a ray. You can consider a ray passing through this focus, the focus on the left side. If if a ray is incident this way, what happens is after passing through the lens, it becomes parallel to the principal axis. And if it becomes parallel to the principal axis, it ends up going like this. And you will see that it will meet the other rays at the same point. Okay. So you can even take an incident ray this way, passing through the focus on the left side. After passing through the lens, it becomes parallel to the principal axis. Okay. But they'll all meet at the same point, and that point is the image location. Okay. Our aim now is to derive an expression for magnification. By definition, magnification is nothing but height of the image divided by height of the object. Okay. Let's call object as AB and image as A dash B dash. Okay, image is smaller than the object in this case. So what we are looking for is A dash B dash divided by AB. That is the magnification now. Okay. But we want to derive a formula for magnification which will be valid in any case of image formation by a lens. So we have to include sign convention in this. Fine. Now, according to the rules of sign convention, distances above principal axis are considered positive, distances below it are considered negative. So if you want to derive something which includes sign convention, you should take it as minus A dash B dash divided by AB. Okay. Now, usually by using the lens formula, we can derive where the image forms. So we'll be knowing the image distance and the object distance. So in the diagram, we know the distance from object to the lens. We call this as the object distance. And we also know the distance from lens to the image. We call that as image distance, V. It will be better if we write the formula in terms of these, U and V. Okay. So we are going to make use of similarity of triangles as usual, as we always do. Call this angle as alpha. Then this angle on the opposite side of the lens will also be alpha. In the left side triangle, which triangle? BAP. You get tan alpha is equal to opposite. Opposite is nothing but AB divided by adjacent is OP. Okay. And right side of the lens in triangle B dash A dash P. Okay. Image and the optical center. If you imagine that right angle triangle, the same tan alpha becomes A dash B dash divided by OP IP. Image to optical center. Equate these two. This means A dash B dash divided by IP is equal to AB divided by OP. That means A dash B dash divided by AB is nothing but IP divided by OP. Fine. IP is image distance, OP is object distance. Now here, I to P is on the positive side. That's fine. O to P is on the negative side. So what we are actually looking for is minus A dash B dash by AB. So magnification is negative of A dash B dash by AB, which is negative of IP by OP. But IP in this case, image to pole, this is actually image distance. You can take it as V as it is. But OP, object to, optical center, not the pole, object to optical center is negative of U. Now the minuses cancel and finally you get the magnification produced by a lens as V divided by U. That's all. Image distance divided by object distance. But you have to use this with proper sign. You have to substitute with proper sign. Then you will get a proper idea of the magnification. Okay, simple derivation. I'll send you the notes. You can go through it. Okay, let's quickly solve one problem based on this. Generally, you all tell me whether it's a mirror or a lens. What does positive magnification indicate?
Bigger than the object, sir.
No. Positive magnification doesn't mean image is bigger than the object.
Virtual and I.
Virtual also you cannot tell. In case of a lens, maybe you can. No, actually, in case of lens also, no. Just because it is positive, you can't decide it is virtual image. You can only say it's an erect image.
Sir, is it in like the
Erect image or upright image, you can say. Okay, let's not even use the word upright. Basically, what it means is that the image has the same orientation as the object. Okay, that is what positive magnification means. And if magnification is negative, it's an inverted image. Image orientation will be opposite to the object orientation. Okay, that's all. That is all positive and negative suggest. Whether it's reflection or refraction, the meaning of positive negative is the same. Next, if magnitude of magnification is greater than 1, that means the image is bigger than the object. Okay, enlarged or magnified image. And if magnitude of magnification is less than 1, that indicates a diminished image compared to the object. Okay. Try this question. Object of height, let's say 2 centimeters, is placed perpendicular to principal axis of a diverging lens, or I don't have to tell you converging divergent, of a lens of focal length minus 20 centimeters at a distance of let's say 40 centimeters from it. Derive the magnification. It's always good if you visualize the ray diagram. Okay, an extended object is placed in front of a diverging lens. Focal length negative means it's a diverging lens. Okay, usually concave lens, when it is placed in air, it behaves as a diverging lens. Okay, so do this all of you. Just a moment, I'll get the image of a diverging lens. Okay, first draw the ray diagram, all of you. An extended object is placed in front of this diverging lens. Its focal length is negative. If you are taking object on the left side, okay, and the focal length is negative, the focus on the left side is what you need to consider. Because if object is on the left side, rays will be going to the right. Right is positive, left is negative, focal length is negative. So this focus is what matters for the ray diagrams. So how do we do ray tracing? We take one ray parallel to the principal axis. The ray parallel to the principal axis bends as if it is passing through the focus. So in this case, since it's a diverging lens, it has to be shown like this. It bends this way. It diverges, means goes away from the principal axis. Okay. And we take another ray straight to the optical center of the lens. That other ray passes without deviation. So this is the second incident refracted ray. And for an observer on the right side of the lens, these two rays will appear to be coming from this common point. So this is where the image forms. We expect the image to be upright, diminished. Okay. Check if the answer you derive also says the same thing. You derive an answer for magnification and tell whether it's upright, diminished or not. Make it fast. Okay, I got one answer as 1/3. Let's see. Magnification produced by a lens is image distance divided by object distance, and we have to substitute them along with sign. Object distance is clear. It is placed 40 centimeters in front of the lens. So object distance will be taken minus 40. Rishi, did you derive the image distance?
No, sir.
Tell me the lens formula.
1 by f is equal to 1 by v plus 1 by u.
No, you told the mirror formula. For the lens formula, 1 by v minus 1 by u is 1 by f. Or you can say, see, like if you solve more problems, you'll get used to this. 1 by u, if you send to the other side, it becomes like this, and this becomes f plus u divided by uf. Therefore, you can write v is equal to uf by u plus f. You can directly use this formula to find out image distance in case of lenses. U is minus 40, focal length is minus 20, divided by u plus f. Minus 40 plus minus 20 is minus 60. 20 and 60 goes 3 times. The answer is minus 40 by 3. This is the image distance. And as expected, it's on the negative side. Okay. Object is at 40 centimeters on the negative side. Image is at 40 by 3 centimeters on the negative side. That's all. Now you substitute them in the magnification formula. Image distance is minus 40 by 3. Object distance is minus 40. Minus 40 gets cancelled. The answer is plus 1 by 3. And as expected, the magnification is positive. What does it mean? Image has the same orientation as the object. And the magnitude of magnification is 1/3. Means the image height is 1/3 of the object height. Object height was how much? 2 centimeters. Therefore, the image height is 2 by 3 centimeters. 1/3 of the object height. Isha, is this clear?
Yes, sir.
Okay. Fine. That is about magnification produced by a lens. Simple formula V by U will tell you the magnification. And based on the sign and magnitude of magnification, you can tell whether it is enlarged, inverted, diminished, upright, and all those things. What about real and virtual? See, we are talking about image formation by a lens. Lens refracts light. Okay. It bends light and the light travels to the other side of the lens. So if image forms on the other side, that means if image distance is positive and object distance is negative. If image distance is positive and object distance is negative, rays actually pass through the image position, and in that case it becomes a real image. Okay, that is how a real image is defined. Light has to actually pass through the image position. Okay. Therefore, in this case, magnification, what will it become? Magnification formula is V by U, no? For a real image, we want V to be positive, U to be negative. That means magnification should be negative. If magnification is negative by a lens, it's a real image. But anyway, don't blindly remember this fact that magnification should be negative. If you visualize the ray diagram, no, then you will know for sure whether it's a real image or a virtual image. If light actually passes through the image location, or if image forms on the other side of the lens, it's a real image. If image forms on the same side from which the light is incident, then it's a virtual image. Because light actually goes to the other side. If image is on this side, then it only appears to be coming from there. It doesn't actually come from there, which is what happened in the last question that we solved. This image is a virtual image. Because light is not actually passing through that point after refraction. Before refraction, yes, one ray was passing that way. But after refraction, the rays are not passing. Okay, they only appear to be coming from there. It's a virtual image.